Assalamu alaikum. Hello, everyone. Before we start from where we left off last time, I would like to revisit this example once more. I spent some time looking into this, and there is something worth mentioning here. Okay, so let me run this again. Okay, so you remember this case study, right? So it's about like cars. Okay, so I don't need to explain it again. You know it from the previous video. Okay, so if you remember, as I said, when we performed PCA, okay, without scaling, we didn't scale this. Okay, then this is what we got, right? So let me, I introduced this scaling code. Let me comment it out for now. Run without scaling, just to remind you. Okay. So this what we got here, right? So the first principal component covers 99.75 or 0.75% of the total variance. Okay, and in fact, this PCA is actually the first PCA is almost the weight feature. Okay, so this is 0.99, and all of the others are almost zero. Okay, so I mentioned that this is because if you look into the weight here, okay, the values are so high compared to others, okay? So it's dominating because of the high values and also the high variance, okay? Because I saw numbers here as low as it's generated random every time we do it. So I saw numbers as high, as low as 1,000 and numbers as high as almost 5,000. So the range is so high, okay, and the variance, of course, is so high, okay, compared to the variance of the other features. So that's why when we cover the variance for this one, okay, we are covering like almost 90, more than 99.75% of the variance. Okay, then this is actually, I don't believe that this is the only feature that matters here. I agree there are some correlations. They are correlated, so there is a room for dimensionality reduction here. Definitely, we don't maybe need all of the seven. We don't need seven features. We can do dimensionality reduction, and we can actually come up with less number of features uh, in order to, if we want to, of course, to create a model that predicts economy from from the input features. Okay, there's a room here for dimensionality reduction. But what I believe is that not to the level like only one matters here. Okay, because in fact, if we normalize, we will see a different, and we did actually. Okay. So the bottom line, there is a room for dimensionality reduction, but not to the point like we are left off with only one feature that covers 99.75% of the variance. I don't think this is the case. And we saw that when we did normalize it, actually. Let's rerun it again and do the normalization. So if we run this again, okay. So wait here. Okay, I will, and I will show you something actually here. I also actually computed the correlation to show you like they are correlated. There is some correlation, but some of them are very strongly correlated to each other, but some are like less correlated. Okay, for example, here, okay, so the correlation between the number of cylinders and the displacement is so high with this, and the number of cylinders and the horsepower is so high, but with the acceleration, okay, it's not so high. Also with the mile per gallon, okay? So the strength, okay, the direction is negative, but the strength is also not as high as this, okay? There is correlation. Definitely there is correlation, but not to the point that we only need only one feature out of all of these, okay? Or we can project to 1D, not to that level. And we actually saw that, okay? Let me, okay, so this is now here we did normalize the features. Now, if we compute the BCAs after the normalization, this is what we get. The first one covers only 72.64% of the variance. Okay, so with the first three, with the first three ones here, we are covering like around 95% of the variance. I believe with these three, if we build a model based on these three, okay, they cover 95% of the 95% of the variance compared to the one we built using the original features was covering 99, right? 99.75. So these, though they cover less, okay, these three, if I build a model based on these three, I haven't done it yet. Maybe I will do it sometime later. I believe we will get a better model in terms of predicting economy from those three BCAs than predicting economy from the only one that covers 99.75% of the variance that was uh, computed using the original unscaled features. Okay, so then scaling is very important. You need to scale. Okay, so to avoid the scenario when one feature is dominating, it's just because of like large values and large variance. Okay, so you want to make sure you normalize. Okay, so you normalize before you perform PCA. Okay, yes, with that, I think we can go to the next thing here. And in fact, now after the normalization, we computed this, right? So if we continue, okay, these are the values we get, the different values. Okay, so there's not like it's not one dominating. Okay, so maybe these are less related ones. Okay, or I would say we can like they have lower weights. They contribute less to the first PCA. In fact, the model maybe is not doesn't really affect the model year doesn't really affect the economy. Okay, class of the car. Okay, and acceleration is maybe it's actually because it's already so correlated to other features that they have high weight. So that's why it has low weight here. Okay. Okay, then let me, that's it. That's what I wanted to say about this example. Let me go to the, what do we, yeah. So let me do it again, just do, I want to consider only two BCAs. Okay, so let's do two. Let's keep it normalized. Okay. So if you do two, then let's comment out this. Anyways, that doesn't change. We are taking only two, and after that, just here, these are the two BCAs we have. Okay, so now we continue here. Now we are here. Okay, so what we are trying to do here, we are trying to actually, we are visualizing things using only PCA1 and PCA2. The conclusions that you can make from this visualization depends on how much you lose from the original data when you project into 2D, because now you're looking at the data into 2D. If there is no so much loss, then maybe this visualization is useful, because whatever you're looking at, it's a good representative of what is going on in the original data, because data could be like very close to 2D, and that lives in a space of 7D. Okay, so this then projecting into 2D and looking into this visualization, whatever conclusions you build could be valid. But if you lose so much when you project into 2D, okay, if the loss is so much, if the data is actually like has higher dimensionality, much higher dimensionality than 2D, then maybe the conclusions you will build from looking into those visualizations will not be valid, because it's not really representative of the original data. Okay, so but now let's just look at the two BCA, first two BCA. For example, in our case here, first two BCAs, they cover almost 90% of the variance. Okay, maybe looking at them is okay. Okay, you can get some information there. So then what we are doing here, we are plotting. So we are plotting scatter plot between PCA1 and PCA2, differentiated by economy. So here we pass palette equal to RPG. So we are defining our own colors for the different classes of economy. If you don't pass this, then the default colors will be used. Okay, so we know this by now, so we don't want to spend so much time on this. So that's the first figure. This one here. Okay, so this is PCA1 and PCA2. Okay, so definitely the PCAs, at least the first two, if we don't go more, then like they are very uncorrelated, because actually that's the goal of principal component analysis, right? So we want to project to like BC like coordinates that cover different angles or perspectives from the data. So they are very uncorrelated, which is good. For the input features, yeah, if you have uncorrelated, that means there's no redundancy here. Okay, so this is what we get. And how do I know if they are by just looking at the figure that they are uncorrelated? So for a given value of BCA1, you can see like BCA2 can take any random value, sorry. So there's no pattern here. There's no like a linear pattern or something in average. Okay, this seems to be very random, the value that BCA takes at a given value, BCA2 takes at a given value for BCA1. Okay, so here maybe you can actually, if you, BCA1 and BCA2 can be used to separate these. Okay, as I said, we are now considering only two BCAs. So we're talking about the separability here at 2D. Okay, it's not, it can do a reasonable job, not so great, not too bad. If we, for example, come up with a line here and maybe another line here, okay, we can predict like those, that we can like maybe a line here, something like this, and a line here. Then whatever after this line is classified as belong to class 0, that any point between these two lines belong to class 1, and any point below this belongs to class 0. We make some errors, but there is some yeah, we can not so high accuracy, but not too bad, I would say. I cannot say more than that. Okay, so now for the second one, what we are doing, we're using origin for the hue. Okay, so can these two BCAs separate the origin? The origin and the economy were not used to compute the BCA, which is, yeah, we can look at the BCA and see if they separate this or not. Okay, let's look at the origin. Here is the origin. There is like here now, the red ones are scattered all over the places. Okay, and there's so much confusion between like the green and the blue ones. That's my. But at least if you put a line here and say like classify everything after this that has belonged to the American origin, maybe for the American ones we can do better job in terms of classifying them. There's confusion between the Asian and the European origins. Okay, these are like the kind of things that you can actually get from looking at the figures. Okay, so here BCA1, BCA2, and we use cylinders for the hue. Okay, so you look at this, there is better uh, separation here, right? Because actually the number of cylinders was used to compute or build these BCAs. Okay, so usually we don't use BCAs to, like, we don't build them from the data and then we use them to separate that data, because they will do good job in your training data. But later on, when you receive a new, in the operation phase, you receive a new sample, you don't have the cylinders, okay? Because when you receive a new sample, then you need to project it into the lower space using the weights we computed, right? But now there is no, the cylinders is not one of the inputs, okay? Then how are we gonna do that? So usually we train BCAs in a number of input features. We use a number of input features to compute these BCAs, which are like a lower dimensionality, or yeah, it's a lower projection of those original features into lower dimensional space. So these features, then we use these to predict the value of a target variable that wasn't used to compute the BCAs. Okay, it's not part of that. Okay. Okay, so let's continue here. Okay, more figures. Okay, if you look at this one here, okay, so we're plotting BCA1 versus BCA2. We use the hue for the economy and style for the origin, and we pass the style is the, like, how the dot or the circle or the point here would look like. Okay, so it's circle for American origin, square for Asian, and diamond for European. Okay, so we are defining those. Okay, and then we're looking, so it's just more things. Okay, so here we are differentiating by two variables. Okay, for example, take this one. Okay, it's green, that means it belongs to class 2 for the economy attribute. Okay, it's from class 2 and the origin is European. Okay, and so the green ones are more of European and Asian, between European and Asian, between square and diamond. Okay, the circle ones are mostly from the American ones, okay? The ones with high, sorry, the red ones. The red ones. The red ones are mostly American, okay? So they have the circle shape, okay? The very economy ones, like the one that belongs to class two, they are between like so the color is green, as you can see. Mostly are either Asian or European cars, okay? Then here, what we are doing here, BCA1 versus BCA2. Okay, let me explain something here. Here, we are actually using a figure level plot, a real plot, okay? So we're plotting BCA1 versus BCA2. We use the hue to differentiate the economy, and we are defining a new thing here called the column. So that means we are generating more than one subplot, okay? So the column is defined by the origin. There are three origins, then there will be three columns. There are three subplots, okay? Three subplots. In one row, three columns, because row is not defined here. So it's one row, three columns. And here we pass the type of the figure as an input argument to real plot, because this is figure level plot, and this is axis level plot. So we pass scatter here. So every subplot, the type of the plot there will be scatter plot. Okay. Okay, so that's it. I think we know the other things. Okay, so yeah, we have already run this. Okay, these are the three subplots here. So this is the origin is American here. We are plotting BCA1 versus BCA2, and the color is used to differentiate the origin. Okay. For example, here, if you look at the European ones here, okay, they are all actually between class one and class two. Okay, for the economy class. Okay. There are no cars from the European that are from European origin that are belong to class zero, okay, for the economy. Same as for the Asian. In fact, for the Asian origin, there are more like cars that are belong to class two. They are very economic, okay? Yeah, these are the kind of things you can look at, okay? And maybe kind of conclusions you can come up with. And if you look more, you'll always be able to come up with more things, okay? But we want to be a bit quick here, okay? So again, real plot, PCA1 for x-axis, BCA2 for y-axis. We use hue for, we use economy to differentiate by the color or the hue. The size of the scatter itself, that depends on the number of cylinders, okay? And we specify the sizes here, the starting and the ending. The style, we use the origin to define the style, and the kind of is scatter, okay? Here, more things, okay? So you can look at those and make similar conclusions. We don't want to waste more time on this, okay? So here, same thing here. Here, there's only one difference. We are introducing row here. Now we have the columns, the number of columns is defined by the different choices for the number of cylinders, and the number of rows is defined by the origin, okay? So there are three origins and number of cylinders, I think four, okay? There will be four columns and three rows. There will be in total 12 subplots, okay? And the type is a scatter, okay? So here we get, so for example, here for the first figure, there are no cars that are from from America, okay? American cars where the number of cylinders is required. This is, by the way, this is normalized, okay? And that's another thing here. When we plot here in terms of the normalized ones, we don't know the original value, okay? We should specify the original value here. It's better if I wrote the original value. I think this is the minimum number of cylinders, which is equal to 3, okay? Yeah, that's one thing. When we did the normalization, I should have taken care of that, because now here, the number of cylinders here, this is actually 0 reflects the first choice. I think it was 3. There were 3, 4. I don't remember. Here, what was the minimum number of cylinders? So when we print it out the first time, okay, maybe the minimum is 4, 4, 6, 8. Okay, so I think there was 3. One of them. Okay, that's a random stuff. So maybe 3, 4, 6, 8. 10. Were there 10? I don't think so. Anyways, whatever the number is, okay? So here we should have plotted actually using the, at least for the labels, we should have used the original number of cylinders, okay? Or also we could have like, maybe we could have excluded the number of cylinders from the normalization. No, I don't know how would that affect, because it's a single digit number. I don't know how would that affect, because now everyone else would be between 0 and 1. Okay, it's better we normalize all to the same range. Okay, but you always can use the original labels. Okay, so here let's look at, assume this is the minimum is 3. So there is no car here that is American and the number of cylinders is 3. Okay, there are some American cars where the number of cylinders is equal to 4, and these cars are mostly like belong to class 1 and class 2 in terms of the economy. Okay, they are economic, more economic than class 2. Remember, class 0 more economic than class 0. Sorry. Okay, so the ones that are American and the number of cylinders is equal to 4, all of them are belong to class between. They are between class 1 and 2. 2 is the most economic ones. Okay, so here when the number of cylinders, the highest one, let's assume this is 8, I don't remember. So then there are American cars there, and mostly they are belong in terms of the economy attribute, they belong to the to class 0. So they are less economic than the least economic ones, and so on. You can look at this and make this kind of conclusions. So let's come to answer these questions here. Can the first two principal components separate economy information? Okay. Okay, so that is by looking at this figure, right? The first two BCAs, okay? This figure, right? They have some separation with some errors, okay? Not so great, not too bad, I would say, okay? So the BCA show good separation with some overlap, yes. Now it looks like PCA can separate cylinders information. Is this a valid conclusion? As we said, it's not a valid conclusion because the number of cylinders was considered when we constructed those BCAs. Okay, we explained that. The principal components correspond to any of the existing variables. In general, that's not the case. They are every one of them is a weighted sum of the existing variables. Okay, so they are, each one is a linear combination of some or all existing variables. Okay, so that's in general. Maybe we stop here for today. Next time we will start the data summarization or data summary analysis. Yeah, that will take like maybe 1 or 2 more videos before we move to the next topic, linear regression. Thanks for watching. Salam alaikum.